Welcome back to Math 104. If we play the game with 15 doors, how does that help us understand the game with only 3 doors? I'm going to select this door right here, and notice that of all the 14 doors I didn't pick, the host chose this one, to leave closed. Now maybe it's just a coincidence that the host happened to pick this door of all the doors to leave closed, or maybe the host left this one closed because that's where the car is. Because there are so many doors, it seems very conspicuous that this is the one door that was deliberately left closed. When I switch, lo and behold, there's the car. There's always a chance that I will just happen to select the door initially that has the car behind it, but it's very unlikely. And if my initial choice has a goat behind it, then what will happen is exactly what happened here. I'm going to see many, many goats, one closed door, and that one closed door will be the one with the car behind it. So the host's decision to leave this particular door closed signals to me that it's very likely that that's where the car is. It's really the same kind of thinking when there are 3 doors. The host is deliberately leaving one door closed, and that deliberate choice to leave one door closed is telling us something. Our last simulation is going to be on this website that lets us run the experiment 100 times, or perhaps even 1,000 times, let's go with 100, and see what happens when we stay with our original choice, that is, keep the original choice. Let's see what happens there. Many more losses than wins, many more goats than cars. Let's do that some more. Let's do that some more. Let's do that some more. After 400 runs of the experiment, keeping the original choice, staying with the original door, it's almost exactly 1/3 of the time giving me a car and 2/3 of the time giving me a goat. What if we run the experiment many times, changing the choice of door? In other words, switching doors. Let's run it 100 times. We see the results here. Now the wins, the cars, are outnumbering the goats by almost 2 to 1. And we can keep going and do another 100 and then another 100. After a total of 400 runs of the experiment, where we are switching doors every time, we're getting a car roughly 2/3 of the time, and the goat roughly 1/3 of the time. When you run the experiment many times, that really helps make it convincing. The pure stayer has a 1/3 chance of winning the car, and the pure switcher has a 2/3 chance of winning the car. What do we conclude from studying the Monty Hall problem? Once again, our first intuitions were not very reliable. It was very easy to think that it shouldn't matter whether you switch doors or not. That seemed so intuitive, but it was incorrect. The Monty Hall problem is a classic puzzle. You can try it out on your friends. There are lots of simulators online. Or maybe you can simulate it in real life with an actual car and 2 goats. Running the Monty Hall experiment repeatedly and collecting data will give you relative frequencies for winning the car by staying, or winning the car by switching. And if you keep running the experiment long enough, it will convince you, or it will help convince you, that the probability of winning if you switch doors really is 2/3 rather than a half. It really does matter whether you switch or not. The conceptual point that makes it all work is that the host's prior knowledge of where the car is represents extra information within the problem. The host is deliberately leaving a certain door closed, and that tells you something. The role of the host's prior knowledge isn't immediately obvious. We had to think about it for a while. But it has a real impact on the probabilities. That's all for the Monty Hall problem. Please go on to the next video, and we'll start talking about statistics.